on a clear night, every star you can see, every faint galaxy captured by a telescope, and every distant point of light drifting through the darkness belongs to only one portion of reality. It belongs to the part of the universe that has been able to reach us. Light does not travel instantly. It crosses space at a finite speed, extraordinarily fast by human standards, yet still limited. And because the universe has existed for a finite amount of time, there is a limit to how far away something can be and still have had enough time to send its light to Earth. That limit surrounds us in every direction, but there is no reason to imagine it as a wall. There is no known barrier waiting at the farthest distance our telescopes can probe. No shell enclosing the cosmos. No sign saying that space ends here. The boundary belongs to observation, not necessarily to existence, and that creates one of the simplest and deepest questions in modern cosmology. What lies beyond everything we can see? To approach that question, we might begin close to home and slowly move outward. First, past the moon, whose light reaches us in a little more than a second. Then beyond the planets, beyond the outer darkness of the solar system, and into the immense distances between the stars. Continue beyond the Milky Way, where hundreds of billions of stars form a glowing island in space. Farther still are neighboring galaxies, then groups of galaxies, enormous clusters, and long filaments containing thousands upon thousands of galaxies. At even greater scales, these structures begin to form something resembling a web. Galaxies gather along vast threads of matter. Between them lie enormous regions with comparatively few galaxies, known as cosmic voids. The pattern stretches across hundreds of millions of light years. And still, we have not come remotely close to the limit of what can be observed. The observable universe extends so far that ordinary intuition begins to fail. The universe is about 13.8 billion years old. It would be natural then to assume that the most distant objects we could possibly see must be no more than 13.8 billion light years away. But the real situation is stranger, because space itself has been expanding while light has traveled toward us. The regions that emitted the oldest light we receive today are now much farther away than the simple age of the universe might suggest. In present-day distance, the radius of the observable universe is roughly 46 billion light years. That means the observable region surrounding us is about 93 billion light years across. This does not mean light somehow traveled faster than light. The photons still move locally through space at the speed of light. But while they were traveling, the space between large-scale cosmic regions was changing. Distances grew. The universe expanded. A photon beginning its journey toward the region that would one day contain Earth could spend billions of years crossing an evolving cosmos, while the location it left behind became enormously more distant. This is one reason cosmic distance is so different from ordinary distance. When we look outward, we are also looking backward. The moon appears to us as it was a little over a second ago. The sun appears as it was about 8 minutes ago. Nearby stars appear years or decades in the past. And when telescopes observe galaxies billions of light years away, they are not seeing those galaxies as they are now. They are seeing ancient versions of them. Some appear younger, less organized, and more active than nearby galaxies, because their light began traveling when the universe itself was much younger. The night sky is therefore not a picture of one universal present moment. It is a collection of different times. The farther we look, the deeper into cosmic history we see. Eventually, Ordinary galaxies disappear from view, not because space ends, but because we are looking back to a time before galaxies had formed. Continue farther into the past, and the universe becomes hotter, denser, and more uniform. And eventually, we reach a period when space was filled with a glowing plasma. During the first hundreds of thousands of years of cosmic history, the universe was so hot that electrons could not remain bound to atomic nuclei for long. Matter existed as an electrically charged mixture, and light constantly scattered from free electrons. The early universe was not transparent. It was more like a dense, glowing fog. Photons could not travel freely across enormous distances. Then, as the universe expanded and cooled, electrons combined with nuclei to form neutral atoms. Light was suddenly able to move much more freely through space. Some of that ancient light is still traveling today. We detect it as the cosmic microwave background. It arrives from every direction, faint and cold after billions of years of cosmic expansion. This is the oldest electromagnetic light we can directly observe. And when maps of the cosmic microwave background are displayed as a sphere around us, it can easily look like the inside surface of some enormous cosmic shell. But that image can be misleading. The cosmic microwave background is not the physical edge of the universe. It is not a wall. It is not a boundary beyond which nothing exists. It is a boundary in time. We are seeing the universe at the moment when it first became transparent enough for that light to travel freely. If another observer existed in a galaxy billions of light years away, they would see their own cosmic microwave background surrounding them. Their observable universe would be centered on them. Ours is centered on us. Neither observer would be located at a special center of reality. This is one of the quiet clues that the phrase observable universe means something very different from universe. Every observer carries an observational horizon around them, and those horizons do not perfectly overlap. A sufficiently distant observer could see regions of space that Earth can never see. At the same time, some regions visible from Earth might lie outside that observer's horizon. So somewhere beyond the most distant light reaching us tonight, there may be regions of the cosmos whose galaxies, stars, and history are completely absent from our sky. Not because they are hidden behind an object, not because our telescopes are too weak, but because their information has simply not reached us. And stranger still, some of it may never reach us at all. That difference between what can be seen and what can ever be reached becomes more important the farther into the universe we look. A galaxy does not need to be close enough for us to visit in order for us to see it. In fact, some galaxies visible in our telescopes are so distant that, under our current understanding of cosmic expansion, a signal sent from Earth today could never reach them. Their ancient light has reached us because it began its journey long ago, when the distances involved were smaller, and the expansion history of the universe was different. But the universe continued to evolve while that light crossed space. The galaxy that emitted those photons may now be vastly farther away. This produces a strange situation. We can receive information from a place that may already be permanently beyond our ability to influence. Observable does not necessarily mean reachable, and the distinction arises because the universe is not static. On the larger scales, it is expanding. When astronomers say that the universe expands, it is easy to picture galaxies flying outward from a central explosion, like fragments from a firework. But that picture is not quite right. The Big Bang was not an explosion from one special location into an already existing emptiness. Instead, the distances between widely separated, gravitationally unbound regions of space have increased as the universe has evolved. There is no known central point from which everything is racing away. From our galaxy, very distant galaxies appear to recede from us, but an observer in one of those galaxies would also see sufficiently distant galaxies receding from them. On large scales, no ordinary location is known to occupy a privileged center. A simple analogy can help, although every analogy has limits. Imagine small marks drawn on the surface of an inflating balloon. As the surface expands, each mark sees the other marks moving farther away. There is no special mark on the surface that serves as the center of the expansion. The center of the balloon exists only because the balloon is embedded in a higher dimensional space, so that part of the analogy should not be taken literally. Cosmology does not require our three-dimensional universe to be expanding outward into some larger surrounding room. What matters is that distances within the universe change. This also explains a famous and initially puzzling fact. Very distant galaxies can recede from us at an effective rate greater than the speed of light. That sounds as though they are violating relativity, but they are not locally racing through nearby space faster than a beam of light. Instead, enough expanding space lies between us and them that the total distance separating us can increase faster than light could cross that distance at one moment. Special relativity still governs local motion. A spacecraft passing another spacecraft nearby cannot simply accelerate through space beyond the speed of light. Cosmic expansion is a different phenomenon, and because the expansion has changed throughout cosmic history, the path taken by light through the universe can be surprisingly complicated. A photon emitted by a very distant galaxy may initially find the distance to Earth increasing, even while the photon is moving in our direction. Later, as conditions change, it may enter regions where it can finally make progress toward us. Eventually, billions of years after beginning its journey, it reaches a telescope. The faint image then recorded by that telescope is the final stage of an extraordinarily long passage through expanding space. This brings us to one of the useful ways cosmologists describe the limits of observation. There is something called the particle horizon. The name sounds more dramatic than the idea itself. The particle horizon is essentially the greatest distance from which information could have reached us during the history of the universe so far. It marks the limit of our causal past. Anything farther away, under the usual cosmological description, has not had enough time to influence us since the beginning of cosmic history. As the universe grows older, this horizon evolves. More time exists for information to travel. In that sense, one might expect that if we simply wait long enough, more and more of the universe should eventually become visible. And to some degree that is true. But there is another horizon that makes the story stranger. It is called the cosmic event horizon. Instead of asking which signals have had enough time to reach us already, the event horizon asks a different question. Which signals emitted now could ever reach us, even if we waited for an arbitrarily long future? Because cosmic expansion is accelerating, there are sufficiently distant regions from which light emitted today may never reach Earth. The distance between us and those regions can grow in such a way that the newly emitted light never succeeds in crossing the expanding gap. So there are two very different limits. One concerns what has been able to reach us from the past. The other concerns what will ever be able to reach us in the future. Between these two ideas lies one of the most unusual features of our cosmic situation. Some galaxies can be visible today through ancient light, while events happening in those same distant regions now may remain invisible to us forever. We are seeing a chapter of their history whose pages left long ago. Later pages may never arrive. The galaxy itself does not suddenly encounter a wall. Nothing special necessarily happens at the horizon from its own local point of view. The horizon belongs to the relationship between distant regions in an expanding universe. This is why cosmic horizons should not be imagined as solid objects floating somewhere beyond the galaxies. If you could somehow travel toward one, you would not expect to see a glowing boundary approaching. Your own observable region would change along with your location. The horizon is defined by which events can exchange information with you. It is a boundary of communication, and once we think of it this way, another quiet mystery appears. Suppose there is a galaxy just beyond the region whose ancient light has had time to reach us. We cannot see it. No telescope can photograph it today. It could be enormous, filled with billions of stars, surrounded by other galaxies, and embedded in a vast continuation of the cosmic web. Yet from Earth, it contributes no image to the sky. Move farther outward and there could be another, and another, perhaps entire galaxy clusters, perhaps enormous voids, perhaps filaments extending across distances larger than anything contained in our current maps. The reason cosmologists consider this possibility seriously is not because such regions have secretly been observed. They have not. It is because the universe we can observe gives no obvious indication that large-scale space should suddenly stop exactly where our access to information ends. Within our observable region, the universe is remarkably consistent on very large scales. The same basic physics appears to operate in distant galaxies whose light has traveled for billions of years. The cosmic microwave background is nearly uniform across the sky, with tiny variations that later help seed the structures we see today. Large-scale surveys reveal the same broad cosmic web in many directions. These observations support what is known as the cosmological principle. It is the idea that, when viewed on sufficiently enormous scales, the universe is broadly homogeneous and isotropic. Homogeneous means that no vast region is expected to be fundamentally unique simply because of its location. Isotropic means that, on large enough scales, the universe has no obvious preferred direction. This does not mean every place is identical. The galaxy cluster is very different from a cosmic void. Earth is very different from the space between galaxies, but average over sufficiently immense distances, and the large-scale properties appear surprisingly similar. That principle allows cosmologists to make cautious inferences beyond the part we directly observe. If the universe continues beyond our horizon, one reasonable expectation is that at least some nearby regions beyond it may resemble the universe on our side of the horizon. There may simply be more cosmic web, more dark matter, more hydrogen, more galaxies forming, evolving, colliding, and fading beneath skies that can never be seen from Earth. But this remains an extrapolation. The farther beyond observation we try to reason, the more carefully we must separate what has been measured from what a model suggests. And we quickly arrive at a question for which there is still no confirmed answer. If the observable universe is only one region inside something larger, how much larger is the whole universe? It might extend modestly beyond our horizon. It might be enormously larger, Or space itself might have no finite total size at all. The possibility that space has no finite total size sounds extraordinary, but it is not something cosmology can simply rule out. When scientists ask whether the universe is infinite, they are not asking whether it has been expanding for an infinite amount of time. The universe can have a finite age, while space itself extends without end. The distinction is important. A universe that began in a hot, dense, early state about 13.8 billion years ago does not necessarily need to have begun as a tiny object surrounded by emptiness. If space is infinite today, then in many standard cosmological descriptions, it may also have been spatially infinite in the early universe, only much hotter and denser everywhere. The Big Bang in that picture happened everywhere. There would be no location toward which we could point and say, that is where the universe began. Every region we see today was once part of that much hotter cosmic state. And regions beyond our observable horizon, if they exist, would have their own ancient history as well. So how could we ever learn whether space continues forever? One clue comes from geometry. On sufficiently large scales, space can have different kinds of curvature. It may be positively curved, negatively curved, or extremely close to what mathematicians call flat. A flat universe is the easiest to picture locally. In ordinary flat geometry, parallel lines remain parallel, and the familiar rules of triangles work as expected. Positive curvature behaves differently. A simplified two-dimensional analogy is the surface of Earth. Two travelers beginning at the equator and heading north along apparently parallel paths can eventually meet at the pole. Negative curvature has yet another geometry, often compared loosely to a saddle-shaped surface. Our real universe has 3 spatial dimensions, so these surfaces are only aids to intuition. The actual geometry of space does not need to curve into some visible, higher-dimensional room. Astronomers can test cosmic geometry by studying patterns whose physical scales can be inferred independently. One of the most useful places to do this is the cosmic microwave background. Tiny variations in that ancient radiation contain information about the early universe. Their apparent sizes on the sky are affected by the geometry through which their light has traveled. Measurements indicate that the observable universe is remarkably close to spatially flat. But there is a subtle point here. Close to flat is not the same as proving that the whole universe is infinite. Imagine standing on an enormous sphere much larger than Earth. If you could examine only a tiny patch beneath your feet, that patch might look perfectly flat. The curvature would become obvious only across a much greater distance. Something similar could be true cosmologically. The universe might have a very large curvature scale, so large that our observable region reveals only a small portion of it. There is also an even stranger possibility. Space could be exactly flat and still be finite. This is where geometry and topology become different questions. Geometry describes local properties such as curvature. Topology describes how the entire space is connected. A familiar two-dimensional example is the surface of a cylinder or a torus. Parts of such surfaces can be locally flat, even though the overall surface connects back to itself. Three-dimensional space can, at least mathematically, possess similarly unusual global connections. In certain models, traveling far enough in one direction could eventually bring a traveler back toward the starting region from another direction. There would still be no wall, no cliff at the end of space, no boundary where the universe suddenly stops. Space would simply connect to itself. If our universe had such a compact topology on a scale small enough to observe, it might leave subtle signatures in the sky. Light from the same distant object could potentially reach us along more than one path through space. In an especially favorable case, the same galaxy might appear in different directions, seen at different ages, because its light had traveled along routes of different lengths. Patterns in the cosmic microwave background might also repeat in distinctive ways. But researchers have searched for signs of this kind. So far, no confirmed pattern has demonstrated that the universe wraps around on scales accessible to us. That does not prove that it does not. If the characteristic size of such a topology were much larger than our observable region, its repetitions could lie permanently beyond what we can detect. And here, we encounter the same limitation again. The observable universe gives us an enormous amount of information, yet it remains only one cosmic volume. We cannot step outside and look back. We cannot move a telescope somewhere beyond our horizon and compare the view. All measurements begin from within the region available to us. This means that a universe can be far larger than our observable patch without leaving an obvious clue about its total extent. Suppose, for a moment, that the entire cosmos is finite, but vastly larger than what we can see. Our observable universe would then resemble a small illuminated region inside an immense landscape. The darkness beyond would not represent empty space. It would simply represent places from which information has not arrived. There might be galaxies there much like the Milky Way. There might be enormous clusters forming at intersections of dark matter filaments. There might be quiet cosmic voids stretching across hundreds of millions of light years. And an observer in one of those remote regions could look outward and see a universe centered on themselves. Their cosmic horizon would overlap ours only partly. Some galaxies familiar to us might appear near the edge of their observable region. Other galaxies, completely invisible from Earth, could fill much of their sky. From their perspective, Earth itself might lie close to a horizon, or even beyond it. This thought experiment reveals something important about the word center. We are at the center of the observable universe from our point of view. But that statement carries no more special cosmic significance than saying you are at the center of everything you can see from the middle of a foggy landscape. Your visible region is naturally centered on your own eyes. Move somewhere else, and the visible region moves with you. The same principle applies on a far greater scale to cosmic observation. Our spherical observable universe is centered on Earth because Earth is where our measurements are being made. An observer elsewhere receives a different sphere of information. There is no contradiction, and there is no evidence that Earth occupies the physical center of all existence. Stranger still, this means there may be no single universal map showing everything that exists at one shared cosmic moment, in the simple way we might imagine. Each observer receives information carried by light from different distances and therefore different times. The farther the source, the older the view. Even within our own observable universe, we never see distant reality exactly as it is now. A galaxy 10 billion light years away may have changed enormously since the light entering our telescopes began its journey. Its stars may have aged. New generations may have formed. Galaxies may have merged. Black holes may have grown. And yet none of those later events can be known to us until their information arrives. For regions sufficiently distant, some of that information may never arrive at all. So when we ask how large the universe is, we are asking about something more difficult than measuring a distant shoreline. We are trying to infer the shape and extent of a reality, while seeing only the portion whose history has been able to communicate with us. And current measurements leave several possibilities quietly open. The universe may be finite and enormously larger than what we observe. It may be finite without possessing any physical edge, or it may extend indefinitely, with no final distance at which space comes to an end. The sky does not yet tell us which of these possibilities is true. If space truly continues without end, then the observable universe would represent only a finite region inside something immeasurably larger. There would be no final galaxy, no last cluster standing beside an outer darkness, and no location where a traveler could arrive at the edge of space and look outward. Space would simply continue. But an infinite universe is only one possibility. Current measurements are consistent with a universe that is extremely close to spatially flat. Yet those measurements cannot tell us with certainty whether the total extent of space is infinite. This uncertainty becomes even more interesting when we ask how the observable region became so smooth in the first place. When astronomers study the cosmic microwave background, they find that its temperature is astonishingly uniform across the sky. There are tiny variations, and those variations are extremely important. Over billions of years, gravity amplified small differences in density until they contributed to the formation of galaxies, clusters, filaments, and the vast cosmic web. But beneath those subtle variations, the early universe was remarkably even. Look in one direction, then turn your telescope toward almost the exact opposite side of the sky, and the ancient radiation has nearly the same temperature. At first this seems natural. Then, we remember what those opposite directions represent. The regions that emitted that light were enormously far apart. In a simple picture of cosmic expansion without an earlier special phase, some of those regions appear to have been too widely separated to exchange light or heat before the cosmic microwave background was released. So why were their conditions so similar? This is known as the horizon problem. It does not mean that the observations are wrong. It means that our simplest picture of the early universe seems incomplete. One leading idea for resolving this puzzle is cosmic inflation. Inflation proposes that, during an extremely early stage of cosmic history, space underwent a period of extraordinarily rapid expansion. This would have happened long before atoms, stars, galaxies, or even the cosmic microwave background existed. The timescale involved was tiny beyond ordinary intuition. Yet during that brief interval, distances could have increased enormously. The important idea is not merely that the universe expanded quickly. It is that regions now separated by distances larger than our observable horizon may once have been much closer together. Before inflation stretched them apart, they could have shared physical conditions. Then the expansion carried them to immense separations. Much later, when the universe became transparent and released the light we now detect as the cosmic microwave background, those distant regions retain the remarkable similarity established earlier. Inflation also offers an explanation for another observation. Our observable universe appears very close to spatially flat. If you take a curved surface and examine an extremely small part of it, that small region can look almost flat. The surface of Earth is curved, but a quiet field beneath your feet does not obviously reveal the curvature of the planet. Inflation can work in a somewhat similar way on cosmic scales. If an initially curved region of space were stretched by an enormous factor, the portion visible to us afterward could appear extremely flat. This does not prove that inflation occurred exactly as any particular model describes. Inflation is a powerful theoretical framework with important observational motivation, but scientists are still studying its mechanism, its duration, and what physical field may have driven it. There are many versions of inflation, and not all make identical predictions. Still, the idea creates a striking possibility for our central question. If inflation stretched space far beyond the region we can currently observe, then everything visible to us today might occupy only a tiny portion of a much larger cosmic domain. The entire 93 billion light-year wide observable universe could be only a small patch inside something vastly more extensive. Our oldest light would then reveal not the boundaries of that larger space, but only the boundaries of the region from which information has reached us. Beyond our horizon, inflationary models often allow space to continue. How far it continues depends on the model. Perhaps enormously farther, perhaps without a finite end, and there may be regions so distant that no single exchange between us and them could ever reveal their existence directly. This produces a peculiar limitation. A theory may describe a larger cosmos, while our observations remain confined to one portion of it. We can test the theory through consequences visible within our region. We can compare predictions with the cosmic microwave background, the distribution of matter, and other measurements. But that is different from photographing what lies beyond the horizon itself. Science can infer beyond direct sight, but inference has degrees of confidence. This distinction matters, especially when we move deeper into the possibilities associated with inflation. Some versions of inflation end everywhere after the rapid early expansion. Other models behave differently. In certain theoretical descriptions, inflation may stop in some regions while continuing in others. A region where inflation ends could evolve into a vast cosmic domain containing matter, radiation, stars, and galaxies. Far away, inflation might still be continuing, eventually producing other domains. This possibility is often called eternal inflation. It is an intriguing extension of some inflationary models, but it is not an observed fact. No telescope has detected another inflationary domain beyond our universe. No spacecraft has crossed into one, and the question of whether such regions could ever leave testable signatures remains an active and difficult subject. This is also where discussions of a multiverse sometimes begin. The word multiverse can sound as though it refers to one single established scientific idea. It does not. Different theories use the word in different ways. In some inflationary models, it refers to extremely large cosmic regions that developed separately after inflation ended locally. Other multiverse ideas arise from entirely different areas of theoretical physics. These possibilities should not be confused with the much simpler statement that space may continue beyond our observable horizon. More universe beyond what we can see does not automatically mean other universes. A galaxy just beyond our particle horizon could belong to the same continuous cosmic space as the Milky Way, governed by the same physical laws and descended from similar early conditions. That possibility requires nothing as exotic as a separate universe. It may simply be a part of our own universe that light has not had enough time to reveal. Far more speculative possibilities begin only when we ask whether extremely distant domains might have different histories, different conditions, or perhaps even different effective laws of physics. Within everything we can currently observe, nature shows remarkable consistency. Atoms in distant galaxies produce the same recognizable patterns of light. Gravity shapes structures across billions of light years. The cosmic microwave background looks extraordinarily uniform. We have no direct evidence that the fundamental laws suddenly change somewhere beyond our horizon. Yet we also cannot observe indefinitely far away to confirm that they never do. And so the cosmic horizon marks more than the limit of our telescopes. It marks a boundary between what can be measured directly and what must be approached through models, inference, and carefully stated uncertainty. Beyond it, reality may remain familiar for distances beyond imagination, or at sufficiently enormous scales. The story may become stranger. For now, the universe gives us no direct view, only a horizon, and the faint ancient light arriving from this side of it. That limitation becomes especially important because cosmology has an unusual problem that most sciences do not face. We have only one observable universe to study. A biologist can examine many cells. An astronomer can compare thousands of stars. A physicist can repeat an experiment under slightly different conditions. But when we measure the largest possible scales of the cosmos, there is no second observable universe beside ours that we can use as a comparison. We cannot move billions of light years away, construct another cosmic map, and ask whether our region is typical. We receive one sky, one cosmic microwave background, one visible arrangement of the largest structures. This creates a fundamental statistical limitation known as cosmic variance. Some patterns in the universe may differ slightly from one enormous region to another, simply because structure formed from small early variations. If we could observe many completely separate cosmic regions of the same size, we might calculate how much those patterns vary, but we cannot. At the very largest scales, the region available to us contains only a limited number of independent structures. That means there are questions for which better telescopes cannot completely remove the uncertainty. A more sensitive instrument can measure our sky with extraordinary precision. It cannot give us another sky. This is one of the quiet boundaries of cosmology. Some uncertainty comes from imperfect technology. Some comes from faint signals. But some may be built into the fact that we occupy only one observable portion of reality. And yet, within that portion, the amount we can see is enormous. Galaxies do not fill space randomly. Gravity, acting largely through an invisible framework of dark matter, has shaped matter into an immense network. There are galaxy groups containing a handful of large galaxies and many smaller ones. There are galaxy clusters containing hundreds or thousands. There are enormous concentrations and extended arrangements sometimes described as superclusters. And on still larger scales, galaxies trace filaments separated by vast cosmic voids. Seen in large surveys, this structure resembles a three-dimensional web suspended through darkness. At the intersections of its filaments, galaxy clusters gather. Along the threads are chains and walls of galaxies. Between them are regions where matter is much more sparse. Some cosmic voids stretch across astonishing distances, containing relatively few galaxies compared with the surrounding filaments. Yet even these gigantic patterns are tiny compared with the full observable universe. A structure hundreds of millions of light years across can sound almost impossibly large, but many such structures can fit within the region whose light has reached us. And our entire cosmic map ends not because the web clearly stops, but because observation itself eventually reaches a limit. This raises a natural question. If we could somehow see a little farther, would the cosmic web continue? current cosmological models generally expect large-scale statistical structure to continue beyond our observable region, at least for some enormous distance, because nothing in the data suggests that our horizon marks a special physical transition. But expectation is not observation. The filaments beyond our horizon have not been photographed. Their galaxies have not been counted. Their voids have not been mapped. We infer their possible existence by extending a successful description of the universe beyond the region where direct evidence ends. This is something science does carefully in many areas. We infer the existence of planets before visiting them. We infer the interiors of stars from light, gravity, and physical theory. We reconstruct ancient environments from traces that survived into the present. Cosmology works in a similar way, but on scales so large that some predictions concern regions from which no direct signal may ever arrive. The strongest inferences are those tied closely to observations. The farther we move from measurable consequences, the more cautious the language must become. And that caution matters when we ask how many galaxies may exist beyond what we can see. Astronomers can estimate the population of galaxies within the observable universe, although the exact number depends on what counts as a galaxy and how many faint systems remain below current detection limits. But there is no scientifically justified number for all galaxies in the entire universe without first knowing the total size of space. If the universe is finite, the total number may be finite, but enormously larger than the number inside our horizon. If space is infinite and continues to contain matter with broadly similar large-scale properties, then the total number of galaxies could also be infinite. The word infinite should be treated carefully here. It is a conditional conclusion, not a measurement. No astronomer has counted an endless chain of galaxies. Infinity would follow from the assumed global structure of space, combined with the way matter is distributed. And an infinite universe produces some unusual thought experiments. If space continues without end, then there may be regions separated from us by distances so enormous that no signal could ever connect them to Earth. Their existence could have no influence on any experiment we perform here. Even so, mathematically, they could belong to the same continuous universe. This makes the phrase "beyond the observable universe" very different from the phrase "outside the universe." Beyond our observable universe may simply mean farther through ordinary cosmic space. Outside the universe is a much stranger question. When someone asks what the universe is expanding into, the everyday meaning of expansion can lead us astray. A cloud expands into surrounding air. A balloon expands into a room. An explosion sends material into nearby space. So it feels natural to assume that the universe must also be expanding into something beyond itself. But standard cosmology does not require that. Cosmic expansion describes changing distances within space. It does not require an external emptiness waiting outside the universe. If the universe is infinite, it can expand while remaining infinite. Distances between sufficiently separated regions increase, even though there is no outer boundary moving into anything. If the universe is finite but unbounded, expansion can increase its overall scale without producing an edge. So the question, what is the universe expanding into? May be asking for a surrounding space that the theory does not need. And the question, what lies outside all space? May not have an ordinary spatial answer at all. This is why the central mystery of our journey must remain precise. We are not yet asking what lies outside reality. we are asking what lies beyond the region reality has allowed us to observe. That question is scientifically meaningful because our horizon is not believed to mark the end of space. And there is another consequence of this distinction. Even inside the universe, we can already observe. We cannot see distant places as they exist at this moment. Every distant image arrives late. A galaxy seen 2 billion light years away is seen through light that began traveling billions of years before it entered our telescope. During that journey, the galaxy continued to evolve. Stars formed and died. Gas moved. Black holes grew. Perhaps galaxies merged. Its present condition is separated from us by the travel time of information. At the greatest distances, this separation becomes immense. So there are really several layers of cosmic unknown. There are places we see only in their ancient past. There are places whose ancient light reaches us, but whose present events may never do so. And beyond our observable horizon may be places from which no information has reached Earth at all. The farther outward we go, the universe does not necessarily become less real. It simply becomes less accessible. And somewhere in that difference between existence and access lies one of the deepest mysteries the night sky can offer. Accessibility becomes even stranger when we think not only about what we can see now, but about what future observers will be able to see. The universe is not merely expanding. Its expansion is accelerating. That conclusion comes from several lines of observation, including measurements of distant supernovae and the large-scale behavior of the cosmos. The simplest description used today includes a form of energy associated with space itself, usually called dark energy. We do not yet understand its deepest nature, but if the current pattern of accelerated expansion continues, it has profound consequences for the distant future. Galaxies that are not gravitationally bound to our local region will continue to recede. Their light will become increasingly stretched to longer wavelengths. Their images will grow fainter, and over immense periods of time, many of them will effectively disappear from view. This does not mean the galaxies themselves vanish. They continue to exist in their own regions of space. The disappearance is observational. Their light becomes so redshifted and so delayed by cosmic expansion that future observers in our part of the universe will no longer receive useful information from them. Our descendants, if observers still exist on unimaginable future timescales, may inhabit a sky that looks far emptier than ours. The Milky Way and Andromeda are gravitationally bound and are expected to merge long before then. Other nearby galaxies belonging to our local gravitational neighborhood may remain connected as well, but distant galaxy groups and clusters will continue to slip away. Eventually, the wider cosmic web visible to us today may no longer be visible from our location. This creates a remarkable historical fact. We happen to live during an era when the large-scale structure of the universe is still observable. We can detect the cosmic microwave background. We can measure galaxies billions of light years away. We can observe expansion across enormous distances. We can study the evidence that the universe was once hotter and denser. A sufficiently remote future civilization might find some of these conclusions much harder to reach. If almost every galaxy beyond its local gravitational system had faded from view, the sky could offer far fewer clues that a vast expanding cosmos had ever been visible. The universe itself would not have become smaller. The accessible evidence would have changed. This is another reminder that an observable universe is not fixed for all time. Its boundaries evolve. As time passes, Light from some previously unseen events can finally arrive. Yet accelerated expansion also places other events forever beyond communication. These two effects happen together. Our particle horizon grows because the universe has had more time for information to travel. But the cosmic event horizon means that some regions will never establish contact with us, no matter how long we wait. The distinction can feel subtle, so it helps to imagine two distant galaxies. From the first galaxy, ancient light may already be on its way toward Earth and may arrive far in the future. From the second, farther region, a photon emitted today may never reach us. Both galaxies might exist within the same continuous universe. Neither needs to cross a physical barrier. The difference lies entirely in the changing geometry between distant places. At very great distances, even the phrase "moving away" can become misleading. A galaxy does not necessarily feel any unusual local force pulling it through space. Locally, its surroundings may appear ordinary. Its stars orbit. Its planets move. Nearby galaxies interact through gravity. Yet on scales large enough that gravitational binding no longer dominates, the average distance between cosmic regions grows. This is why cosmologists often describe expansion in terms of the scale of space rather than galaxies simply flying outward. The distinction also helps explain why there's no obvious center. If everything were moving away from one explosion point through a pre-existing emptiness, we could imagine tracing all trajectories backward until they converged on one location. But cosmic expansion does not work that way in standard cosmology. Trace the universe backward, and the distances between widely separated regions shrink everywhere. Matter becomes denser everywhere. Temperatures rise everywhere. The early hot state was not sitting at one coordinate inside today's universe. It filled the space from which today's observable region evolved. And if space extends beyond our current horizon, then those more distant regions also trace back toward their own part of that same early cosmic state. This point becomes especially useful when thinking about what the Big Bang looked like. There was no giant fireball expanding into black emptiness, with galaxies eventually appearing on its outer surface. The Big Bang describes an early condition of the universe itself. Space, matter, and radiation were all in a much hotter, denser state. Expansion then increased distances between unbound regions. So when we ask what lies beyond the observable universe, we should not picture ourselves sitting inside a glowing sphere with unknown darkness outside it. A better picture is quieter. We occupy one visible patch within a larger cosmic history. Our horizon is drawn by the paths information is taken to reach us. Move to another galaxy, and the patch changes. Move sufficiently far, and entirely new regions become visible, while some of ours fall away. In that sense, the universe may contain countless overlapping observable regions, each centered on a different observer, not separate universes, not isolated bubbles necessarily. Simply different windows onto one larger space-time. And this leads to an almost poetic, but scientifically precise idea. There may be galaxies that are part of the universe we describe, formed from the same broad cosmic processes, obeying the same laws, and embedded in the same large-scale structure. Yet no signal from them will ever enter any telescope on Earth. Their stars may shine for billions of years. Their planets may orbit in silence. Their galaxies may collide, merge, and transform. And none of those events need ever become part of our observable history. The universe can contain real events that remain permanently outside our information. This is not a failure of telescopes. It is not a problem waiting for a sufficiently powerful instrument. A larger mirror can gather fainter light. A more sensitive detector can reveal weaker signals. But no technology can receive information that space-time never allows to arrive. That is the deeper meaning of a cosmic horizon. It is not the limit of engineering. It is the limit of causal connection. And once that idea is clear, the title question becomes more difficult. What lies beyond what we can see? Perhaps more of the same cosmic web. Perhaps an unimaginably larger continuation of the universe. Perhaps regions produced under conditions we can only infer. And perhaps, at some distances, domains whose existence can never be tested directly from here. The mystery is not only that the universe may be larger than what we see, it is that some of that larger reality may be permanently beyond every future observation we could ever make. Once we accept that some regions may remain permanently beyond observation, another question appears. How can science say anything meaningful about them at all? The answer is that science does not require direct sight in every case. Much of what we know about the universe comes from indirect evidence. We cannot travel inside a star, yet we understand a great deal about stellar interiors because the physics of pressure, temperature, gravity, nuclear reactions, and light all fit together consistently. We cannot watch the earliest moments of cosmic history with ordinary light, yet we can test models of those moments by looking for traces they may have left behind. Cosmology often works this way. It begins with what can be measured, builds a mathematical description that successfully explains those measurements, and then asks what else follows from that description. The farther the prediction extends beyond direct observation, however, the more carefully we have to speak. This is especially true when thinking about the universe before the cosmic microwave background was released. The microwave background is often described as the oldest light we can see. That is correct in a specific sense. It is the oldest electromagnetic radiation that can travel to us freely from the early universe. But it does not mark the beginning of cosmic history. The universe had already existed for hundreds of thousands of years, before those photons began streaming freely through space. Earlier than that, the cosmos was filled with hot plasma, light constantly scattered from charged particles, so the universe was opaque. If you could somehow stand in that early environment, there would be no clear view across vast distances. Radiation and matter were interacting too frequently. Go still farther back in time, and conditions become even hotter and denser. Atomic nuclei had not yet formed. Earlier still, even protons and neutrons were not assembled in the familiar way. The farther backward our models reach, the more extreme the energies become, and the more difficult the physics becomes to test directly. Ordinary light cannot carry us through that opaque era, but other messengers may someday offer clues. One possibility involves gravitational waves. These are ripples in space-time produced when masses accelerate in certain ways. Astronomers have already detected gravitational waves from events such as merging black holes and neutron stars. But much earlier gravitational waves, if they were produced in the young universe, could in principle carry information from epochs that electromagnetic radiation cannot reveal directly. A primordial background of gravitational waves has not yet been conclusively detected. If one were found, it could open a new window onto some of the earliest accessible moments of cosmic history. There are other indirect clues as well. The relative abundances of light elements, such as hydrogen and helium, preserve information about conditions when the universe was only minutes old. The distribution of galaxies preserves traces of tiny early density variations. The cosmic microwave background preserves an extraordinarily detailed record of the universe when it became transparent. Each observation reaches backward in a different way. Together, they create something like cosmic archaeology. The deeper we look, the fewer direct witnesses remain, yet the surviving evidence can still constrain what probably happened. This same method allows scientists to think cautiously about regions beyond the observable horizon. We cannot see them, but we can ask whether the physics observed inside our horizon gives any reason to expect a sudden boundary just beyond it. So far, it does not. The universe appears highly uniform on large scales. The same physical constants describe distant regions within our observable volume. The same broad processes seem to have shaped matter across billions of light years. This makes it reasonable to expect that the nearest regions beyond our horizon may resemble the regions just inside it. That expectation is stronger than a random guess, but it is still an extrapolation. And there is always the possibility that the larger universe contains structures or conditions we cannot infer from our limited sample. One reason this question remains open is that the observable universe may be much smaller than the whole. If so, then everything we see could represent only one local patch inside a much larger cosmic landscape. A useful analogy is weather. If you stood in one enormous valley and could never leave it, you might learn the local climate with great precision. You could measure temperature, rainfall, wind, and seasons for centuries. Your model might become extremely accurate, but you would still need caution before assuming that every valley across an unseen continent had exactly the same conditions. Cosmology is far more constrained than this analogy suggests, because the laws of physics and the large-scale uniformity we observe provide powerful guidance. Still, the principle remains. A finite observational region cannot automatically reveal every global property of the whole. This is why cosmic topology is so difficult to determine. Suppose space connects back to itself on a scale just slightly larger than what we can observe. We might see no repeating pattern at all. The repetitions would occur beyond our horizon. Our local measurements could still show space to be almost perfectly flat. Nothing nearby would reveal the global connection. Or, suppose the universe is infinite. No finite observation could demonstrate infinity directly. We could measure curvature ever more precisely and find no evidence of closure. We could extend galaxy surveys deeper. We could map the cosmic microwave background with extraordinary accuracy. Yet there would always remain a logical difference between saying, "We have detected no edge," and saying, "We have proven there is no edge anywhere." The first is observational. The second is global. And the observable universe may never give us enough information to make the second statement with certainty. There is something peaceful in this limitation. Science is not weakened by admitting where measurement ends. In fact, one of its strengths is the ability to separate what is known, what is strongly inferred, and what remains uncertain. The observable universe is filled with remarkably precise knowledge. We can measure its expansion. We can reconstruct much of its history. We can study structures formed billions of years ago. We can detect photons that have traveled across almost the entire age of the cosmos. Yet the total size, global shape, and full extent of reality remain unsettled. And the strange part is that better instruments may not solve every one of these mysteries. Some questions may be limited, not by the weakness of our telescopes, but by the structure of space-time itself. There may simply be no path by which the required information can reach us. If that is true, then the universe contains a permanent frontier of knowledge. Not a frontier marked by a wall. Not a place where matter stops, but a quiet boundary beyond which events remain causally disconnected from our world. And somewhere beyond that boundary, the larger universe may continue without ever becoming part of the sky we see. A permanent frontier of knowledge does not mean that the universe becomes meaningless beyond it. It means only that our connection to those regions is limited. And one of the best ways to understand that limitation is to think about two observers who are separated by an enormous distance. Imagine an observer living in a galaxy tens of billions of light years from us. From that galaxy, the universe would not look like our observable universe. Shifted slightly to one side, it will be centered on them. They would receive ancient light from regions that Earth cannot see at all. Their telescopes might reveal galaxies, clusters, voids, and filaments that have never contributed a single photon to any instrument near the Milky Way. At the same time, some parts of our own observable universe might be hidden from them. The two observers would inhabit the same larger cosmos, yet their visible realities would only partially overlap. This is one of the most important ideas in cosmology. The observable universe is observer-dependent. It is not a fixed ball floating somewhere in space. It is the region from which information has been able to reach a particular observer. Move the observer, and the observable region changes. This helps explain why Earth can appear to sit at the center of a vast sphere without occupying any special physical position. Every observer is at the center of their own past light cone. Every observer receives information from all directions. Every observer naturally sees a roughly spherical horizon around themselves. The sphere comes from the finite speed of light and the finite age of cosmic history, not from a central place in the universe. This also makes the cosmic microwave background easier to understand. When we look outward in any direction, we eventually reach light, released when the universe became transparent. Because that light has had nearly the same amount of cosmic time to travel toward us from all directions, it appears as a surrounding spherical surface. But another observer far away would see a different surface centered on their location. The two surfaces would overlap in complicated ways. Neither would be a shell surrounding all of reality. They are simply the places in space-time from which ancient photons happen to be reaching each observer now. The same logic applies to galaxies. A distant galaxy might lie near the edge of what we can currently observe. For us, its light might be arriving after a journey of more than 13 billion years. For another observer much closer to that galaxy, it would not appear ancient at all. They might see it at a much later stage of its evolution. They might see neighboring galaxies invisible to us. They might also receive information from directions that our own horizon excludes entirely. There is no single cosmic viewpoint from which the whole present universe is laid out at once. Every observer sees a different combination of distance and time. That is because distant observation is always delayed. The farther away something is, the older the information we receive. This is easy to forget because nearby life does not make the delay obvious. When you look across a room, the travel time of light is so tiny that the scene seems instantaneous. Across the solar system, the delay becomes measurable. Across interstellar distances, it becomes years. Across the universe, it becomes billions of years. A telescope, therefore, does not simply show where distant things are. It shows where they were and what they were like when the light began its journey. The deepest images of galaxies are also images of cosmic youth. Some distant systems appear irregular and turbulent because we are seeing them during eras when galaxy formation was much more active. Some of the stars in those galaxies may no longer exist. Some of the galaxies may have merged into larger systems. Their current condition cannot be known from the ancient light arriving now. In a very real sense, the farther universe is hidden from us twice. First, there are regions beyond our observational horizon that we cannot see at all. Second, even within the region we can observe, we cannot see distant places in their present state. We see a layered history. This is why cosmologists sometimes describe observation in terms of a light cone. As time passes, light from more distant events can enter our view. But what becomes visible depends not only on distance, but on the structure and expansion of space-time. And accelerated expansion complicates the picture. There are galaxies whose ancient light we can see today, but whose present-day light may never reach us. The version of the galaxy visible in a telescope can therefore belong to a chapter of cosmic history that remains observable, even while later chapters are permanently inaccessible. This leads to a quietly remarkable thought. There may already be events taking place in distant parts of our observable universe that Earth will never know about. Stars may be forming, galaxies may be merging. Entire civilizations, if any exist, could rise and disappear. Yet if those events occur beyond our cosmic event horizon, the information they produce now may never arrive here. We do not lose that information because it is destroyed. It simply never crosses the expanding distance between us. This is a different kind of unknown from an unsolved scientific problem. An unsolved problem might yield to better equations, more precise observations, or a new experiment. But causally inaccessible events may remain inaccessible in principle. No larger telescope changes the geometry of space-time. No detector can collect a photon that never arrives. And this means the universe may contain far more history than any single observer can ever reconstruct. Each observer has access to only a portion of the cosmic story. A distant observer may eventually learn things we never can. We may observe regions forever hidden from them, and there may be still more distant places beyond both horizons, visible to neither. If the universe is sufficiently large, this pattern could continue across distances beyond imagination. Overlapping spheres of observable history, each centered on a different location, none contained in the whole. The larger universe, whatever its true size, would then be less like a single picture waiting to be seen, and more like an immense reality from which every observer receives only a local archive. The strange part is that this archive changes with time. New ancient light arrives, some distant sources fade, horizons evolve, and the universe that can be known from any one location slowly changes along with them. So the question of what lies beyond the observable universe has no single boundary drawn permanently in space. The boundary depends on where you are, when you are observing, and which signals space-time allows to reach you. Beyond our horizon may lie places that are invisible to us, but perfectly ordinary to someone else. And beyond theirs, perhaps still more. The universe does not need to stop where information stops. It may simply continue into regions belonging to other horizons, other skies, and other histories that ours will never contain. If every observer receives only a local archive of the cosmos, then one of the deepest questions becomes almost unavoidable. What is the shape of the larger space that contains all these overlapping horizons? At first, the word shape may suggest that the universe must have an outline, like a sphere floating in something larger. But cosmologists mean something more subtle. They are asking about the geometry of space itself, on very large scales. Does space behave as though it is flat? Does it possess positive curvature? Does it have negative curvature? And separately from curvature, could it connect back to itself in some unexpected way? These questions matter because different global geometries can lead to very different answers about what lies beyond our observable region. A positively curved universe could, in some models, have a finite total volume while possessing no boundary. The familiar analogy is the surface of Earth. Earth's surface has a finite area, yet if you travel continuously along the surface, you never reach an edge where the ground simply stops. You eventually return toward where you began. Of course, the surface of Earth is two-dimensional, while cosmic space has three spatial dimensions. The universe does not need to be the inside or surface of an ordinary sphere in some surrounding room. The analogy is useful only because it demonstrates that finite does not automatically mean bounded. Space could, in principle, contain a finite amount of volume without possessing an outer wall. Negative curvature offers another possibility. In a negatively curved geometry, spatial relationships differ from familiar flat geometry in another direction. Such a universe could naturally extend indefinitely, although curvature alone does not always determine the complete topology. And then there is flat space. Measurements of the cosmic microwave background and other cosmological observations indicate that the portion of the universe we can observe is extremely close to spatially flat. This is one of the reasons an infinite universe remains entirely possible, but there is a catch. Flatness does not prove infinity. A flat space can sometimes be connected globally in such a way that it has a finite volume. To see the idea, imagine an old video game in which a character walking off the right side of the screen reappears on the left. The screen itself may look completely flat. Locally, nothing unusual happens, yet opposite sides are connected. Three-dimensional space can have mathematical versions of this kind of connection, although they are much harder to visualize. In such a universe, moving continuously in one direction could eventually return you to your starting region from another direction. You would never encounter a border. You would simply discover that space closes through its topology. If the universe had this kind of compact structure on a scale smaller than, or not much larger than our observable region, it might reveal itself through repeating patterns. Light could travel around space by more than one route. A distant galaxy might, in principle, be visible in multiple directions because its light reached us along different paths. The images would not necessarily look identical. One path might be longer than another, meaning we could see the same galaxy at different ages. What look like two unrelated distant objects might actually represent one system due to different journeys of light. The cosmic microwave background might carry even clearer clues. If space connected to itself on observable scales, certain large-scale patterns in that ancient radiation could repeat. Cosmologists have searched for signatures of this sort. So far, no convincing detection has established that the universe has a small repeating topology. That result is useful. It tells us that if space does wrap around in certain simple ways, the characteristic scale must be large enough to have escaped the searches performed so far. But it does not tell us that the universe cannot wrap around at all. The repeating scale could simply be larger than our observable horizon, and if it is, the evidence we need may lie precisely where we cannot reach it. This illustrates a recurring difficulty. We can measure local and observable geometry with increasing precision, but global topology is harder. A small patch of a very large structure may not reveal how the whole thing is connected. If you somehow lived on an enormous curved surface while being able to explore only a tiny neighborhood, you could measure that neighborhood carefully and conclude that it looked almost perfectly flat. You might remain unaware that the full surface eventually closes. The observable universe could place us in a similar position. Our cosmic region is extraordinarily large by any human standard. Yet it may still be small compared with the scale required to reveal the full geometry of space. And this is where the question of infinity becomes especially elusive. No telescope can observe infinity. No map, however deep, can contain an infinite amount of space. If surveys continue to find galaxies farther and farther away, that demonstrates that space extends at least that far. It never demonstrates that space extends forever. Infinity is therefore not something astronomers expect to photograph. It is a property that may be inferred from a successful global model. The opposite problem also exists. Failing to find an edge does not prove that the universe has no finite size. A finite, unbounded universe would contain no edge to find. So several very different universes could look remarkably similar from inside one limited, observable region. One could be infinite. Another could be finite, but vastly larger than the horizon. Another could have an enormous, compact topology whose repeating structure lies beyond our reach. For observers on Earth today, each might produce nearly the same visible sky. That is one reason the total size of the universe remains unknown. We are not simply missing a more powerful telescope that can reveal the answer next year. The information needed to distinguish some possibilities may exist only at scales larger than the region causally available to us. And yet the question is not empty. Every new measurement narrows the range of possibilities. More precise observations of cosmic curvature tell us how large any curvature scale would have to be. Searches for repeating patterns constrain possible topologies. Studies of the cosmic microwave background test models of the early universe. Galaxy surveys reveal whether large-scale structure behaves as expected. Piece by piece, the visible universe tells us something about the invisible continuation beyond it. But it does so indirectly. We stand inside one region of space and use the faint patterns carried by ancient light to infer the architecture of something that may extend unimaginably farther. And even after all those measurements, two possibilities remain beautifully difficult to distinguish. Space may continue forever, or it may eventually return upon itself without ever giving us an edge to discover. Whether space continues forever or eventually connects back to itself, everything we can currently observe occupies only one enormous but limited region. Inside that region, matter has arranged itself into structures on almost every imaginable scale. There are planets around stars, stars gathered into galaxies, galaxies collected into groups and clusters. Clusters themselves sit within a much larger pattern of filaments, walls, and voids extending across hundreds of millions of light years. This vast arrangement is known as the cosmic web. Its existence is one of the clearest signs that the universe was never perfectly smooth. The cosmic microwave background shows tiny variations in the density of the early universe. They were extremely small, but gravity had billions of years to amplify them. Regions containing slightly more matter attracted more matter, dark matter, which does not emit light but interacts gravitationally, played a central role in building this invisible framework. Gas flowed into the growing concentrations. Galaxies formed within them over immense stretches of time. The nearly uniform young universe developed the complicated structure we observe today. The result is not a random scattering of galaxies through empty space. On very large scales, galaxies tend to trace long filaments. Those filaments meet at dense nodes where galaxy clusters can form. Between them lie vast cosmic voids. Some voids are tens or even hundreds of millions of light years across. They are not completely empty. A few faint galaxies may still exist within them, along with thinly distributed matter. But compared with the luminous filaments around them, they can appear astonishingly sparse. If you could somehow place yourself deep inside one of the largest voids, the nearest major concentrations of galaxies might be separated from you by distances difficult to imagine. And yet even an enormous cosmic void is only a small feature compared with the full observable universe. The same is true of the largest known galaxy structures. Names such as superclusters, walls, and large quasar groupings sometimes make them sound as though they might approach the scale of the entire cosmos. They do not. They are patterns within the observable region. Beyond them lies more structure, then more, until our surveys eventually become limited by distance, faintness, and cosmic time. At sufficiently great distances, we are no longer seeing the mature cosmic web as it exists today. We are looking so far into the past that the large structures have had less time to develop. This makes maps of the distant universe unusual. Increasing distance changes both the location being observed and the era being observed. A nearby region shows us a relatively recent cosmic structure. A much farther region shows us an earlier stage. At the deepest levels, galaxies themselves give way to the much smoother universe preserved in the cosmic microwave background. So even our largest maps cannot simply display the entire observable universe at one common moment. They are three-dimensional maps mixed with time. And then the map stops. Not necessarily because matter stops. Not because the cosmic web reaches a final filament. Stops because there are regions whose information is unavailable to us. If the cosmological principle remains approximately valid beyond the horizon, and one expectation is that large-scale structure continues there too, there may be additional filaments extending through unseen space. More clusters may occupy their intersections. More enormous voids may separate them. The pattern may continue for distances vastly greater than the diameter of the observable universe. But this is again an inference. No survey has crossed a horizon. No telescope has directly mapped a filament lying entirely beyond the observable universe. The expectation comes from the remarkable consistency of the region we can measure. This raises a subtle question. If the universe is very much larger than our observable region, could some remote areas be dramatically different? Simply because the earliest fluctuations happened differently there? Even without changing the laws of physics, enormous regions could have different arrangements of matter. One region might contain an unusually large concentration of clusters. Another might contain especially extensive voids. The cosmological principle does not require each enormous patch to be an exact copy. It describes statistical similarity when averaged over sufficiently large scales. This means that beyond our horizon, there could be landscapes of galaxies we would find unfamiliar, while still following the same underlying physics. The difference between variation and different physical laws is important. Within the observable universe, the fundamental behavior of nature appears strikingly consistent. Light from distant atoms carries recognizable spectral signatures. Gravity behaves in ways that fit the same broad theory across cosmic distances. No convincing evidence shows that basic constants of nature suddenly take completely different values in another direction. Beyond the horizon, however, we cannot perform the same tests. Some speculative models allow the possibility that extremely distant domains could have experienced different physical conditions. In certain theories, quantities that appear constant within our region might take other values elsewhere. But there is currently no direct evidence that this actually occurs beyond our observable universe. It remains a theoretical possibility in some models, not a discovery. This distinction becomes especially important when people speak about a multiverse. The idea is sometimes presented as though cosmologists have looked beyond our universe and found others. Nothing like that has happened. There are several very different concepts that receive the label multiverse. Some arise from versions of eternal inflation. Some appear in other areas of theoretical physics. Some concern regions of space-time so distant that they may never be observable from our location. And not all of these ideas have the same scientific status. Eternal inflation, for example, emerges naturally from some models of inflation. In those models, inflation might end in one region while continuing elsewhere. The region where inflation ends could become a vast expanding domain with matter, radiation, and eventually galaxies. Other regions might undergo a similar transition at different times. The resulting picture can contain many enormous domains separated by distances or conditions that prevent ordinary communication between them. This is one route by which the word multiverse enters cosmology, but it remains speculative. Inflation itself has substantial theoretical motivation and fits important features of the observed universe. Yet the precise mechanism that drove inflation remains unknown. Eternal inflation is an additional step beyond that, and claims about separate cosmic domains are more uncertain still. There is something useful in keeping these layers apart. The statement that the observable universe is probably not the entire universe is much more modest than saying that other universes exist. The first follows naturally from how observational horizons work and from standard cosmological models. The second depends on additional theoretical assumptions. Beyond our horizon may simply be more of our own universe, more ordinary space, more galaxies, more dark matter, more cosmic web, more regions that began from conditions broadly similar to those that eventually produced the Milky Way. We do not need another universe to place something beyond the edge of our observation. The observable horizon already gives us an unseen continuation to think about. And perhaps the most surprising part is how ordinary that continuation could be, far beyond every telescope. There may be nothing dramatic marking the place our view ends. A galaxy could sit just beyond our horizon without knowing that it occupies a special location from our perspective. Its stars would continue to orbit. Its neighboring galaxies would continue to interact. Its own observers, if any existed, would look outward into their own enormous visible cosmos. For them, our hidden region might be the mystery. And somewhere between these overlapping horizons, the universe could continue quietly, without any observer possessing a view of the whole. If no observer can see the whole universe at once, then even the idea of a complete cosmic map becomes surprisingly complicated. A map usually suggests a single arrangement of places existing together, but astronomy never gives us that kind of view directly. The farther away we look, the farther back in time we see. So every deep image of the universe is also a historical record. Nearby galaxies appear relatively recent. Distant galaxies appear younger, and at the greatest visible distances, we approach an era before mature galaxies had even formed. This means that the observable universe is not simply a sphere filled with objects as they exist today. It is a sphere filled with information arriving from many different ages. The outermost regions are also the oldest views. This creates an unusual question. What does a very distant galaxy look like right now? For sufficiently remote objects, we cannot know directly. Suppose a galaxy appears to us as it was 10 billion years ago. Since that light began its journey, the galaxy has had 10 billion years to evolve. It may have merged with neighboring galaxies. Many of its stars may have died. New stars may have formed. Its central black hole may have grown. Its entire appearance may be completely different, yet the version entering our telescope tonight is still that ancient one. The present state of the galaxy exists beyond our current access to information. This is not because the galaxy is beyond the observable universe. It may lie well inside it. The limitation comes simply from light travel time. So even before reaching the cosmic horizon, the universe already contains a vast hidden present. There is an enormous difference between what exists now and what we are able to see now. At small distances, this difference hardly matters. At cosmic distances, it becomes fundamental. And stranger still, accelerated expansion means that for some galaxies, their present condition may never become visible to us at all. We might continue receiving older and older portions of their history for a very long time. But there can be a limit beyond which later signals never arrive. The galaxy remains real. Its future continues locally. Our view simply becomes increasingly detached from it. This is one reason the phrase observable universe deserves careful attention. It does not mean everything that exists now within a fixed distance. It means the region of space-time from which signals have been able to reach us. That distinction between space and space-time matters. A distant event is defined not only by where it happens, but also by when it happens. Two events occurring in the same distant galaxy at different times may have completely different relationships to us. Light from one may eventually arrive. Light from a much later event may not. The boundary of what can be known is therefore not a simple static sphere. It is shaped by the entire expansion history of the universe. This also explains something that often sounds paradoxical. There are galaxies we can observe today that are now farther away than the distance at which recession reaches the speed of light. That does not mean their light should be unable to reach us. The photons we receive today began traveling long ago. While they traveled, the expansion rate changed. The distance between us and their source evolved. Cosmological horizons cannot be understood by imagining a photon racing against a galaxy through unchanging space. The space between them changes too. A photon can therefore begin its journey in a region whose distance from us is increasing extremely rapidly and still eventually arrive, depending on the evolution of cosmic expansion. This is another reason. Simple statements like anything receding faster than light is invisible are incorrect. Cosmology is more subtle. Some currently visible galaxies have recession rates greater than the speed of light in the cosmological sense. Their ancient light nevertheless reaches us. Again, no object is locally breaking the speed limit established by relativity. The expanding geometry changes the distance between widely separated locations. There is an even deeper consequence. The part of the universe visible today is not exactly the same as the part visible billions of years ago, and it will not be exactly the same as the part visible billions of years from now. Our cosmic view is temporary. Every civilization observing from any location and any era receives its own version of the universe. An observer living when the cosmos was much younger would have had a smaller particle horizon. Less time would have existed for distant information to arrive. An observer living unimaginably far in the future may have had more cosmic time, yet accelerated expansion may have removed many distant galaxies from practical observation. So, there may be a particularly rich period in cosmic history when the large-scale universe is unusually accessible. We appear to live within such a period. The cosmic microwave background is still measurable. Billions of galaxies remain visible. The large-scale pattern of cosmic expansion can still be reconstructed. Distant supernovae can still reveal how that expansion has changed. The broad cosmic web remains open to observation. Far in the future, many of those clues may fade. Their loss would not change the past. It would change what future observers can infer about the past. A civilization living in an isolated, gravitationally bound group of galaxies trillions upon trillions of years from now might look outward and see almost nothing beyond its local environment. If it had no surviving record from earlier eras, reconstructing the full history of cosmic expansion could become much more difficult. The visible universe might seem small, dark, and static, yet beyond its observational reach, immense regions of space could still exist. This thought reveals something almost counterintuitive. Knowledge of the universe depends partly on when you happen to observe it. Physical reality has its own history, but evidence does too. Signals arrive. Signals fade. Horizons change. Information that is accessible during one cosmic era may become inaccessible in another. Our present view of the universe is therefore not just a place, it is an opportunity. For a brief span in cosmic terms, ancient light from enormously distant regions is still reaching us in abundance. We can observe galaxies at many stages of development. We can measure the faint background left from the era when the universe became transparent. We can watch the expansion written into the redshifts of distant objects. And from those signals, we can infer that the visible universe is almost certainly not a physical container with a boundary surrounding it. It is a temporary window. Beyond that window, space may continue through distances we cannot measure. And as cosmic time moves forward, even parts of the universe now visible through that window will slowly pass beyond future contact. As parts of the universe pass beyond future contact, the meaning of distance becomes even less intuitive. In everyday life, a distant place is still a place we could imagine reaching, given enough time. A mountain across a continent may be far away, but there is no fundamental boundary preventing the journey. Cosmic distance is different. On sufficiently large scales, there are regions for which waiting longer does not necessarily improve our chances of reaching them. The expansion of the universe changes the journey itself. Suppose we send a beam of light toward an extremely distant galaxy today. Locally, that light always travels at the same familiar speed. Nothing can overtake it nearby, but the space separating us from the galaxy continues to evolve while the light travels. If the galaxy lies beyond the relevant cosmic event horizon, then the increasing distance can prevent our signal from ever arriving. The beam never slows down. It never encounters a wall. It simply travels through an expanding space-time in which its destination remains permanently out of causal reach. This is one of the strangest distinctions in cosmology. A region can exist within the same universe, follow the same broad physical laws, and yet be permanently inaccessible from here. There may be no route by which information sent now could ever cross the separation. In that sense, the universe contains not only enormous distances, but different domains of possible communication. Some places are connected to us now. Some are visible only through very ancient light. Some may become unreachable in the future, and some may always remain outside any possible exchange of information. These boundaries are not visible from space itself. A traveler near, one would not see a glowing surface. There would be no sudden change in the stars. The horizon is defined by relationships between events, not by a physical object. This is why the word horizon is so useful. A horizon is a limit to what can be seen or influenced from a particular position. On Earth, the landscape continues beyond the visual horizon. The cosmic version is more profound because, unlike an ordinary horizon, some cosmic horizons cannot simply be crossed by traveling toward them. The geometry evolves along with the journey. Still, the analogy reminds us of one central idea. A horizon does not automatically mean an edge. And if we follow that thought outward, we arrive at another question. Could today's observable horizon reveal more of the universe in the future? In one sense, yes. As cosmic time passes, light from some events that is still traveling toward us can finally arrive. Number 1. Our particle horizon continues to evolve. Future observers can, in principle, receive information from events whose signals have not yet reached Earth today. But this does not mean the entire universe will eventually become visible. Accelerated expansion prevents that simple outcome. Some regions are so distant that their later light will never arrive, so the future does not steadily uncover every hidden layer of reality. It reveals some things while permanently losing access to others. There is a curious balance between more time and more separation. The universe becomes older, giving light longer to travel. At the same time, large-scale expansion can carry distant regions farther beyond causal contact. This is why the phrase, "if we waited forever," does not solve the mystery of what lies beyond our cosmic horizon. Even an infinite amount of waiting would not necessarily deliver information from every place. Depending on the long-term behavior of dark energy and cosmic expansion, some events may remain forever outside our observable history. That limitation also affects what we mean by the future of distant galaxies. A galaxy we see tonight may continue evolving for billions of years, but there is no guarantee that its later story will ever reach us. Its ancient image may be preserved in our sky, while its more recent reality slips permanently beyond communication. The photons entering a telescope now can therefore feel like messages from a relationship that is already changing. They left when the universe was younger. They crossed expanding space, and by the time they arrived, the region that produced them may have become causally unreachable. There is no tragedy in this. It is simply part of the geometry of an accelerating universe. The cosmos does not organize itself around the needs of any observer. Information arrives when space-time permits it, and the scale of that process becomes almost impossible to picture when we move from individual galaxies to the cosmic web. Imagine two enormous galaxy clusters separated by a vast void. Today, ancient light from both may reach us over extremely long periods. The distance between our gravitationally bound region and those clusters continues to grow. Their light shifts toward longer and longer wavelengths. Their visible activity slows from our perspective. Signals become weaker. Eventually, they fade beyond practical detection. The filaments connecting the large-scale universe appear to dissolve from our view, not because the structures themselves disappear, but because their information becomes increasingly inaccessible. One by one, remote regions leave the observable story available to future observers here. If this continues long enough, the visible cosmos from our location will become dominated by the structures that remain gravitationally bound nearby. the immense web that currently fills deep astronomical surveys will no longer be evident. Yet that future emptiness would be deceptive. A future observer might look into a nearly blank sky while unimaginable amounts of cosmic structures still exist beyond the horizon. The difference would be entirely one of access. And this brings us back to the central question from another direction. What lies beyond the observable universe? The answer may depend partly on when the question is asked. Our present horizon reveals one portion of cosmic history. A much earlier observer would have seen less. A far future observer may see a dramatically emptier cosmos. Each would describe an observable universe shaped by their own place and era. The larger reality could remain far more extensive than any of those views suggest. So the observable universe is not only a region in space, it is a changing region of possible information, and beyond it may lie an enormous continuation of space, whose light either has not reached us yet or never will. If some regions will never send us information, then the universe may contain places that are permanently real to themselves and permanently unknowable to us. This idea becomes especially interesting when we return to inflation. Inflation was introduced to help explain why the early universe appears so smooth and why its geometry is so close to flat. In many versions of the theory, a tiny region of very early space expanded by an extraordinary factor in an extraordinarily short time. That stretching could have taken a region that was once causally connected and made it vastly larger than the universe we can observe today. If so, then the entire observable universe may be only one small piece of a much larger region produced during inflation. This is a difficult scale to imagine. The observable universe already contains billions upon billions of galaxies. Its present-day radius is roughly 46 billion light-years, yet inflationary scenarios can allow the total inflated region to be vastly larger than that. How much larger depends on the model. There is no direct observation telling us the complete size, and this uncertainty creates an important distinction. Inflation can suggest that our observable region is only a small part of a larger whole, without telling us exactly what that whole looks like. The space beyond our horizon might continue with conditions broadly similar to those we see here. It might contain the same kinds of matter, the same kinds of galaxies, the same large-scale cosmic web. If inflation stretched one connected region far beyond our horizon, then the simplest nearby continuation could be remarkably ordinary. But some versions of inflation lead to a much stranger possibility. In certain models, inflation does not end everywhere at once. Instead, it can stop in some regions while continuing in others. Where inflation ends, the enormous energy associated with that phase may be converted into matter and radiation, allowing a hot, expanding cosmic region to develop. Elsewhere, inflation may continue. Later, it may end in another region, and then another. This idea is known as eternal inflation. The word eternal here does not necessarily mean that every location inflates forever. It means that the overall process can continue indefinitely in some parts of the larger spacetime, even while it ends locally in others. The resulting picture is sometimes described using the language of separate cosmic domains, or bubble universes. But that phrase can easily create a misleading image. It is tempting to picture glowing bubbles floating inside a larger empty room. That is not necessarily what the mathematics is describing. These would be regions of space-time within a theoretical cosmological structure, not soap bubbles drifting through ordinary space. And most importantly, eternal inflation remains unconfirmed. It arises naturally in some models, but we do not have direct observational evidence that such distant domains exist. This is where scientific language matters. It is reasonable to say that some inflationary theories allow a much larger cosmos containing many causally disconnected regions. It is not reasonable to say that astronomers have discovered countless other universes. They have not. The distinction becomes even more important because the word multiverse is used for several different ideas. Sometimes it refers to distant regions produced by eternal inflation. Sometimes it refers to possibilities arising in high-energy physics. Sometimes it is used more loosely for any collection of domains that cannot communicate with one another. These concepts are not all the same, and they do not all have the same connection to observation. For our central question, the most conservative possibility remains much simpler. Beyond the observable universe may be more of the same universe, more space, more galaxies, more regions formed from the same broad early conditions. Only after moving farther into theoretical possibilities do we reach ideas about domains with significantly different physical properties. Some models allow that possibility. If the physical state established after inflation differed from one vast region to another, then certain effective properties of physics might also differ. Perhaps a quantity that appears constant throughout our observable universe could take another value somewhere else. Perhaps the kinds of stable particles or interactions could differ under some speculative frameworks, but nothing in our observations demonstrates that this happens beyond our horizon. Within the observable universe, the consistency of physics is striking. The same atomic transitions appear in light from distant galaxies. The same basic gravitational behavior helps explain systems separated by billions of light years. A cosmic microwave background shows a universe that was remarkably uniform at early times. There are ongoing tests for possible variations in fundamental constants, but no established evidence tells us that an unseen region beyond the horizon follows radically different rules. So when we wonder whether physics itself might change beyond what we can see, we are moving from strong extrapolation toward speculation. That does not make the question meaningless. It simply changes the level of confidence we should attach to the answer. This boundary between inference and speculation is one of the most interesting features of cosmology. We can observe only one cosmic region, but theories often describe much more. Some predictions can be tested inside our horizon, even if the theory also describes unobservable regions. Others may be much harder to distinguish from ideas that leave no measurable trace here, and that leads to a deep scientific debate. If a proposed region can never affect us, never send us a signal, and never leave any observable consequence within our horizon, what evidence could establish that it exists? There is no single simple answer. Physicists evaluate entire theories, not isolated imaginative possibilities. A larger theoretical framework may make successful predictions we can test, while also implying features beyond direct observation. But the inaccessible features themselves remain less certain than the tested predictions. This is why the most distant reaches of cosmology demand unusual humility. The mathematics may allow many possibilities. Observation may favor some over others. Yet, there can remain a gap between describing what could exist and knowing what does exist. And nowhere is that gap wider than beyond the cosmic horizon. Perhaps the unseen continuation is almost identical to our own region. Perhaps inflation has created distances so enormous that our visible cosmos is only one tiny patch. Perhaps more exotic domains exist far beyond any possible communication. Or perhaps some of those theoretical possibilities describe nature incorrectly. For now, the sky remains silent about the answer. Everything we know directly still comes from this one observable region, carried to us by ancient light crossing a universe whose full extent remains hidden. That hidden extent becomes especially difficult to think about when we consider one of the largest possible questions. If the universe is infinite, What does infinity actually mean? In everyday life, infinity is usually a word for something merely very large. A long road can feel endless. A night sky can seem limitless. But mathematical infinity is not simply an enormous number. It means there is no final distance, no last region, no outermost galaxy beyond which space stops. If space is truly infinite, then no matter how far you travel, there would always be more space ahead. This possibility is entirely compatible with the fact that the universe has a finite age. The age tells us how long cosmic history has unfolded since the early hot state. It does not automatically determine how much space exists. An infinite universe could have been hotter and denser everywhere in the past, while remaining infinite in extent. This is one reason the popular image of the Big Bang as a tiny point expanding into emptiness can be so misleading. If space is infinite today, it may not have begun as one small ball with an outside. Instead, the entire infinite region could once have been in a much denser state. Expansion would then mean that distances between unbound locations increased everywhere. There would be no outer surface rushing into a surrounding void, and there would be no center. If this picture is correct, then beyond our observable horizon lies not a mysterious boundary region, but simply more universe. And beyond that, more again, perhaps endlessly. The trouble is that no observation can directly confirm infinity. A telescope can show that the universe extends farther than some distance. A more powerful telescope can push the observed boundary deeper. But every observation covers only a finite region. Even if we mapped every galaxy visible in every direction with perfect precision, we would still be studying only the portion whose light can reach us. Infinity always lies beyond any finite map. So when cosmologists say that an infinite universe is possible, they are describing a global property consistent with current observations, not something that has been directly seen. The same caution applies to an intriguing consequence sometimes discussed in connection with infinity. If space extends forever, and the large-scale distribution of matter remains statistically similar across it, then there could be unimaginably many galaxies, possibly an infinite number. And if there are endlessly many regions, some people ask whether distant regions might eventually repeat. Could there be another galaxy arranged almost exactly like the Milky Way? Could there even be another planet with a configuration extremely similar to Earth? This idea sounds like science fiction, but versions of the argument can arise from mathematics. If a finite region can occupy only a finite number of distinguishable physical configurations, and if an infinite universe contains infinitely many such regions, then repetition may follow under certain assumptions. But the assumptions matter enormously. We do not know whether the relevant number of possible physical states is finite in the necessary way. We do not know whether the universe is infinite. We do not know whether matter continues with the same statistical properties across arbitrarily large distances. And even if repetition occurred, the distances involved could be so absurdly enormous that the repeated regions would remain forever outside any possible observation. So, the idea of another identical Earth should not be treated as an established prediction. It is better understood as a late consequence of a particular set of assumptions. The scientific mystery is not that copies of us definitely exist. The mystery is that the total extent of space may be so large that familiar intuitions about uniqueness become difficult to apply. A finite universe can be equally strange. Suppose space has a finite total volume but no boundary, then there may still be no final galaxy and no physical edge. Traveling far enough could, in some possible topologies, eventually return you to a region you had visited before. The journey could be extraordinarily long. It might require crossing distances vastly larger than the observable universe. And because cosmic expansion continues while you travel, the practical possibility of completing such a journey could be very different from the mathematical description. Still, the geometry would contain no wall. This is an important lesson. The question: where does the universe end? We may assume that an end must look like the edge of an object, but space does not need to behave like an object inside a larger room. It can be finite without a boundary. It can be infinite without expanding into anything. And our current observations do not yet tell us which global possibility nature has chosen. This uncertainty also affects the question of how much larger the universe might be than the observable part. Cosmological measurements can constrain curvature. The closer space appears to perfect flatness, the larger any possible curvature radius must be. That can tell us that some finite models would need to be much larger than our observable region, but it does not provide a simple maximum size. The whole universe could be moderately larger than what we see. It could be thousands or trillions of times larger in volume. It could extend on scales for which those comparisons become almost meaningless. Or it could have no finite total size at all. We simply do not know, and there is something unusual about that answer. Modern cosmology can measure the age of the universe with remarkable precision. It can describe the abundance of ordinary matter, dark matter, and the component driving accelerated expansion. It can reconstruct the growth of cosmic structure. It can measure tiny fluctuations in radiation released more than 13 billion years ago. Yet one of the most basic questions imaginable remains open. How much space is there? The difficulty is not that scientists have forgotten to measure it. The difficulty is that the answer may depend on regions lying permanently beyond measurement. We can examine the geometry available to us. We can search for repeated patterns. We can test models of inflation and cosmic expansion. We can narrow possibilities. But a horizon separates local knowledge from global certainty, and so the universe may be presenting us with a question whose complete answer is larger than the information any one observer can ever receive. Somewhere beyond the oldest light in our sky, space may continue for another 100 billion light years, or vastly farther, or without end. Nothing visible at the horizon tells us where that continuation stops. Perhaps because it never does. Perhaps this is where the question finally becomes quiet enough to leave unanswered. What lies beyond the observable universe? The most cautious answer is also one of the most remarkable. Probably more universe. How much more? We do not know. It may continue for distances vastly greater than the region visible from Earth. It may have a finite total size so enormous that its global shape is hidden from us. It may connect back to itself in ways too large for any repeating pattern to appear in our sky. Or space may simply continue without end. None of these possibilities requires a wall beyond the most distant galaxies. The observable universe was never such a wall. It is a boundary created by information. Every object we know through astronomy has revealed itself, because something was able to travel from there to here. Usually that messenger is light. A photon leaves a star, a galaxy, or an ancient cloud of glowing plasma, and begins crossing space. Sometimes the journey lasts seconds, sometimes years, sometimes billions of years. Along the way, the universe changes. Galaxies evolve. Space expands. The wavelength of the photon stretches. Yet eventually, in the cases available to us, that small piece of information reaches a detector. And for a brief moment, something unimaginably distant becomes part of what we know. the deepest light in our sky has traveled through almost the entire history of the universe. The cosmic microwave background carries an image of a time when there were no stars illuminating the darkness and no galaxies arranged into filaments. It reaches us from every direction, but it does not mark the edge of reality. Beyond the matter that released those photons was more matter in the young universe. Beyond our present horizon may now be regions that have developed for billions of years since then. Perhaps those regions contain galaxies not fundamentally different from the ones visible in our deepest surveys. Perhaps they contain enormous clusters surrounded by dark matter. Perhaps long filaments pass around voids so large that their scale would be difficult to comprehend. Even if we could map them, there may be countless places from which our own observable universe would look like a distant, partly hidden region. An observer there would stand at the center of a different cosmic horizon. They might see galaxies that will never appear in our sky, and perhaps the Milky Way would be beyond theirs. Neither observer would possess the complete view. Each would see only the history that had been able to reach them. This is one of the gentlest ways to think about our place in the cosmos. We are not located at the center of everything, but we are necessarily at the center of what we can observe. The distinction is simple, and it changes the picture completely. The sky surrounds us because information arrives from every direction. The horizon surrounds us because light has had only a limited cosmic history in which to travel. Nothing about that arrangement requires existence itself to end when the signals do. There are questions beyond this point that cosmology may continue exploring for generations. Measurements of the cosmic microwave background may become more precise. Galaxy surveys may cover greater volumes. Gravitational wave astronomy may reveal new information about the early universe. Better observations may tighten the limits on cosmic curvature and rule out more possible topologies. New theories may explain inflation more deeply, or perhaps replace parts of our present understanding with something better. But there may always remain a difference between knowing our observable region extraordinarily well and knowing the complete universe. As cosmic variance reminds us that we have only one observable sample, horizons remind us that some information cannot reach us. Accelerated expansion reminds us that even parts of the universe visible today may not remain accessible forever, and the finite speed of light ensures that astronomy will always be an act of looking backward. Every night sky is therefore an archive. The stars above us are slightly younger versions of themselves. The nearest galaxies are historical images. The most distant galaxies are glimpses of eras billions of years gone, and behind them lies the faint ancient radiation from a universe still waiting for its first stars. Farther back than ordinary light can take us, we reconstruct rather than directly see. Farther away than our horizon allows, even reconstruction becomes more uncertain. Eventually, our map fades into inference, and then into possibilities. There's no failure in that fading. A scientific map does not need to pretend that unknown territory has been measured. It can end honestly. It can tell us where observations remain strong, where theory becomes important, and where several possibilities are still allowed. Perhaps that is what makes the observable universe such a beautiful concept. It gives us both an enormous amount of knowledge and a clear reminder of its limits. Within our horizon, we can trace almost 14 billion years of cosmic history. We can watch galaxies forming across time. We can study the geometry of space. We can detect the afterglow of the early universe. We can measure the quiet acceleration separating distant regions. And from all of this, we have learned something that could easily have remained hidden. What we can see is not necessarily all there is. Tonight, the darkness between the stars may seem empty, but some of that darkness represents distance, some represents time, and at the deepest limits of observation, darkness can also mean that no information from farther away has ever reached us. Beyond it, space may continue. No sudden border, no final wall, no last point of light announcing the end, only more distance, perhaps filled with galaxies whose light will never enter our sky. Perhaps still farther regions beyond those? Perhaps a universe so large that our entire observable cosmos is only one small accessible patch within it. Or perhaps space continuing endlessly without any final location from which one could turn around and see the whole. We may never know its complete extent, but the boundary of observation is not the same as the boundary of existence. And somewhere beyond everything visible tonight, beyond the oldest light and the farthest horizon our instruments can reach, the universe may simply continue. Silently, enormously, and unseen.